Let's take a look at this problem where we want to solve a linear system using the inverse of the coefficient matrix. So the coefficient matrix has the first column of 2, 3, 1, 2. Those are the coefficients of x. A second column of -2, -1, -1, -1, coefficients of y. A third column of 4, 9, 2, 6, coefficients of z, and a fourth column of 7, 6, 3, 5. Those are coefficients of w. And then after writing those columns, we write a vertical line and we put the 4 by 4 identity matrix right of the vertical line. So we want to start by getting our zeros in column 1. So I circled where we're in red the entries we want to become 0. So when we're getting the zeros in column 1, we don't change row 1. So I recopied that. We're going to change row 2, row 3, and row 4 so that we get zeros in the circled entries. So I'm going to need to multiply row 1 by 3, -3, and add that to 2 times row 2 to get my new row 2. So the entries in row 2 will be 0, 4, 6, -10, -9, -3, 2, 0, 0. And so you can check that that's actually true. You can pause the video and check those calculations. Now we're going to get a new row 3 by doing row 1 minus 2 times the previous row 3. So we're looking at the previous matrix, and notice we get a new row of 0, 0, 0, 1, 1, 0, -2, 0. And now we're going to get a new row 4 by doing row 1 minus row 4. So that becomes 0, -1, -2, 2, 1, 0, 0, -1. So notice that what we do every time is we start from the leftmost column and we move to the right, getting zeros in the appropriate non-diagonal locations of each column. So in column 2, we want zeros in row 1, row 3, and row 4. So we're not going to change row 2. We're going to use row 2 as our anchor row to get those 0 entries that we desire. So we are going to change row 1 and row 4, but notice we already have a 0 in row 3 in column 2, so we'll just recopy row 3. We don't have to make any changes to that. So we're going to get a new row 1 by adding the previous row 2 to 2 times the previous row 1. We're going to get a new row 4 by adding the previous row 2 to 4 times the previous row 4. So our new row 1 becomes 4, 0, 14, 5, -1, 2, 0, 0. And you can pause the video and check that those calculations are correct. Our new row 4 is 0, 0, -2, -1, 1, 2, 0, -4. And now we're going to get our entries of 0 in column 3. We want all the non-diagonal entries in column 3 to be 0, and I've circled those in red. All right, so now we're going to get a new row 1 by adding row 2 to 2 row 1. Oh, actually, what we're going to do here is we're going to interchange row 3 and row 4 because row 3 is what we want row 4 to be. So we're going to simply interchange row 3 and row 4 here. And now we're going to get our 0 entries in column 3. So we circle the entries we want to become 0. We recopy row 3 because when we're getting our zeros in column 3, we don't change row 3. Row 4 already has a 0 where we want it. So all we're going to do is recopy row 4, and we're going to change row 1 and row 2. So we're going to multiply row 3 by 7 and add that to row 1 to get a new row 1. We're going to multiply row 3 by 3 and add that to row 2 to get our new row 2. So our new row 1 is 4, 0, 0, negative 2, 6, 16, 0, negative 28. And our new row 2 is 0, 4, 0, negative 12, 0, 8, 0, negative 12. And you can pause the video and check that those calculations are correct. Now we want our 0 entries in column 4. So we are not going to be changing row 4 when we get our zeros in column 4. So we recopy row 4. We are going to change row 1, row 2, and row 3. And we're going to get a new row 1 by multiplying 2 times row 4 and adding that to our previous row 1. We're going to multiply 12 by the previous row 4 and add that to row 2 to get a new row 2. And to get a new row 3, we're going to add row 4 from the previous matrix in row 3. So our new row 1 is 4, 0, 0, 8, 16, negative 4, negative 28. Our new row 2 is 0, 4, 0, 0, 12, 8, negative 24, negative 12. And our new row 3 is 0, 0, negative 2, 0, 2, 2, negative 2, negative 4. All right, so now we have all of the zeros that we need. We always get the zeros first, and then finally we get the ones. That allows us to avoid fractions in our calculations. Fractions lend to errors, so we want to avoid them when possible. So we're now going to multiply row 1 from the previous matrix by row 1/4, and we get our new row 1. 1/4 times the previous row 2 gives us our new row 2. Negative 1/2 times our previous row 3 gives us our new row 3. And then we recopy the previous row 4. And now to the right of the vertical line, we have the inverse of our coefficient matrix, which I'll refer to as A inverse. So A inverse has a first column of 2, 3, negative 1, 1, a second column of 4, 2, negative 1, 0, a third column of negative 1, negative 6, 1, negative 2, and a fourth column of negative 7, negative 3, 2, 0. And we are going to multiply that by the matrix of constants, which are on the right side in our system. I'll call that matrix B. That's a column matrix. And we see that those constants on the right side of the system of equations were 10, 12, 4, and 9. So we're going to multiply that column matrix by our A inverse. So we're going to calculate A inverse B. And notice the first row of A inverse gets multiplied by that column matrix. The second row of the inverse gets multiplied by the column matrix. So does the third row of the inverse matrix. And we also multiply the fourth row of the inverse matrix by the column matrix. And we get these listed calculations. So we wind up with another column matrix. So a 4 by 4 matrix times a 4 by 1 matrix gives us a 4 by 1 matrix. And notice that when we do the calculations in the first row, that gives us 1. The calculations in the second row give us 3. In the third row give us 0. And in the fourth row give us 2. So we have our solution. The solution to the system is x equal 1, y equal 3, z equals 0, and w equal 2.